All right. Hello, everybody. I got a question this week regarding this problem from the homework. And it asks a series of questions, but to start out, it wants to know on what intervals is the function f of x equals 7 sine x plus 7 cosine x on the interval 0 where x is greater than or equal to 0 and less than or equal to 2 pi, increasing or decreasing? Or where is it increasing and where is it decreasing? So to answer any kind of question where it's asking for the local minimum or maximum or the interval of increase or decrease, regardless of what the original function is, you're going to want to take the derivative of it and set it equal to 0. So let's get started doing that here. So to take the derivative of trig functions, what I like to do is I like to draw up a little trick that a professor here at Valencia taught me. His name is Niraj Wag. He's a really excellent professor. He teaches Calc 2. So if Professor Karkinen isn't teaching that next semester and you're taking it, I'd recommend him. And what he recommends is he says you should set up this little circle of s's and c's. The s represents sine and the c represents cosine. And if you go clockwise, that is what happens when you take the derivative. Counterclockwise is what happens when you take the antiderivative, but we're not doing that right now, so it's not important. So what we can do is we can apply that to our original function. So using that, we know that f prime of x equals 7 sine x. Sine goes to cosine, so 7 cosine of x plus 7 cosine of x, and cosine goes to negative sine, so we get negative 7 sine of x. So now that we've found our derivative, we're going to set this equal to 0 and solve for x. So 7 cosine of x minus 7 sine x equals 0. Now something we can do here is we can divide everything by 7, and that'll just get rid of these 7s, because 0 divided by 7 is still 0. So this simply becomes cosine of x minus sine of x equals 0. Now from here, I want to add sine of x to both sides, giving us cosine of x equals sine of x. Now, from here we can solve for x by simply knowing where on the unit circle do cosine and sine equal each other. Let me draw a little unit circle right here to just represent what I'm talking about. So, where sine and cosine equal each other is where tangent equals 1. So, sine and cosine equal each other right here at pi over 4. And they equal each other right here at 5 pi over 4. Very good. So from here, we can set ourselves up a number line. Let me write that over here. And remember, our bounds are 0 to 2 pi. So our leftmost point will be 0, and our rightmost point will be 2 pi. And the areas we need to check are bound by pi over 4. So I'll put that right here, pi over 4, and 5 pi over 4, which goes right here. All right, so from here, we want to go ahead and pick some test points. For what's to the left of pi over 4, the test point I want to choose is 0, because that is an option. It is included, as it says up here. In the middle, I'm going to pick a nice easy number for trig functions, pi. And to the right, I'm going to pick 2 pi, because again, that's allowed. So from here, all we got to do is we got to plug all of these into our f prime of x function. And our answers will determine whether the slope is increasing at this point or decreasing, and for each of the respective points, naturally. So first, let's go ahead and test f prime of 0, because that is our first test point. So f prime of 0 equals 7 cosine of 0 minus 7 sine of 0. Now this simply equals 7 times 1, which is 7, minus 7 times 0, which is 0, and that is positive 7. So that is positive. So I'm going to write that right here, little positive on this part of our number line. Next, I need to test our second test point, which is pi. So f prime of pi equals 7 cosine of pi minus 7 sine of pi. And that simply equals 7 times 0, which is 0, minus 7 times 1, which is 7. And our answer is negative 7, which is, of course, negative. So we put a little negative right here in our number line. Now, finally, we're going to test our final test point, which is 2 pi. So f prime of 2 pi equals 7 cosine 2 pi minus 7 sine of 2 pi, which gives us the same thing as our first one, which is 7 minus 0 equals 7, which is positive. So finally, we have the last little area on our number line filled in. So what does that tell us? That tells us that on this section of the number line, our slope is increasing, on this section it's decreasing, and on this section it's increasing. So, based on that information, we know that our interval of increase will be from 0 to pi over 4, and we'll put a bracket for the 0 because it is included, so 0 to pi over 4, with a parentheses on that side, union 5 pi over 4 to 2 pi. 5 pi over 4 to 2 pi, and again another bracket. So this is our interval of increase. Now for our decrease, the only part on this number line where it's decreasing is right here between pi over 4 and 5 pi over 4. So let me write that right here. Decrease is from pi over 4 to 5 pi over 4. And there we have it. Those are our intervals of increase and decrease. Now, from here, we also want to know where our local minimums and local maximums are. So to find this, I'm going to redraw our number line down here, just to make this a little easier to conceptualize. 0 to 2 pi, 5 pi over 4, and pi over 4. Now, if you remember from up above, we know that our slope is increasing here, decreasing here, increasing here. So I'm going to copy that back down here. Increasing, decreasing, increasing. Now, I'm going to draw a dotted line above so I know where this is happening. And it goes from increasing to decreasing to increasing. So we'll see that this will be our local maximum, and this will be our local minimum. Now, to find where these local mins and maxes occur, we're going to need to plug these into our original f function. So let's go ahead and do that. Let me see here. All right, so we'll take f of pi over 4 equals, where is our f function? So f of x equals 7 sine x plus 7 cosine x. So 7 sine of pi over 4 plus 7 cosine pi over 4. And this equals, what does this equal? 7 over 2 square root of 2 plus 7 over 2 square root of 2. And when we add these together and simplify, that simply gives us 7 square root of 2. So this is our local max. Oh, how long has that been off screen? Hope not too long. So there we go. This is our max right here. Now we simply do the same thing for this point right here, which we know is our local minimum. So let me move this over. Let me stop moving it over so it doesn't go off screen actually. So f of 5 pi over 4 equals 7 sine 5 pi over 4 plus 7 cosine 5 pi over 4. Now from here, this time it turns out to be negative 7 over 2 square root of 2 minus 7 over 2 square root of 2, which equals, again, after we add these two together, negative 7 square root of 2. And that is our local minimum. So there we have it. Now that we have found our local mins and maxes, we want to find our inflection points, or points of inflection, so POI, as I call them. And to do this, we need to start by finding the second derivative. When you're looking for the points of inflection or concavity, you need to work with the second derivative. So if you recall, our first derivative was simply 7 cosine of x minus 7 sine of x. And we're going to use that same little trig compass I used earlier to figure this out. There we go. Meaning our second derivative simply becomes minus 7 sine of x minus cosine of x, or minus 7 cosine of x, excuse me. There we go. And now, just like we did for finding the local mins and maxes, we're going to set this equal to 0 and solve. So 0 equals negative 7 sine of x minus 7 cosine of x. And just like we did last time, we can get rid of the 7s, and this time we're going to get rid of the negative 7s actually, so divide everything, both sides, by negative 7, and we get 0 equals sine of x plus cosine of x. So from here, we subtract cosine from both sides, and we get sine of x equals minus cosine of x. Now here, we need to do the same thing we did for the last part of the problem and ask ourselves, where on the number line does sine of x equal negative cosine of x? Well, that happens anywhere where tangent is negative 1. So let me draw another little unit circle right here. Not as nice as my last one, but still do workable. There we go. And sine of x equals negative cosine of x right here at 3 pi over 4. And right here at 7 pi over 4. So from here, we're going to make another number line just like we did last time. And actually, we already know our points of inflection. They're these right here. But I'm just doing this for my own self for later use. So 3 pi over 4 and 7 pi over 4. Now, our points of inflection, POI, for this is 3 pi over 4 and 7 pi over 4. In terms of points on a graph, it's 3 pi over 4, comma 0, and 7 pi over 4, comma 0. So those would be our points of inflection. And finally, we want to find our concavity. And to do that, we're going to go ahead and pick some test points, exactly like we did for the last part. I'm actually going to pick the same ones I used last time too. Oh, I forgot to write the 2 pi down here. And then we just plug these into our second derivative. So I'm going to find f double prime of 0, which is negative 7 sine of 0, minus 7 cosine of 0. And that winds up equaling 0 minus 7, which is, of course, negative 7, which is negative. We're going to write that right here. I'm going to take f double prime of, what am I taking? Pi. That's our second test point. So minus 7 sine of pi minus 7 cosine of pi. That winds up equaling 7 minus 0, which equals 7, which is, again, positive. So write that right there on our number line. And now finally we're doing our final test point, which is 2 pi. So f double prime of 2 pi, which is the same thing as f double prime of 0, but I'll write it out just to make it clear. So negative 7 sine of 2 pi minus 7 cosine of 2 pi. And that, again, equals 0 minus 7, which equals negative 7, which is negative. So I'll write that right here. So when it comes to concavity, wherever, whatever section of the number line is negative, that is where it is concave down. And whatever section on the line is positive, that is where it is concave up. So by looking at this, we can say that it's concave down on this section of the number line and this section, and it is concave up on this section. So you may feel free to write that in interval notation if you like. But as far as points of inflection, concavity, local mins and maxes, and intervals of increase and decrease go, that is all you have to do for this problem. I hope that was a help. I'll talk to you guys later.